Blueprint. Hello and welcome to Energy Decarbonization Blueprint. My name is Dee Carawan and I am co-chair of Santa Barbara AIA COTE. Our speaker today is Jeannie Huntsman, AIA, and she is the Director of Client Relations at Willdan with over 20 years experience as a licensed architect and energy consultant. In her current role, she collaborates with utility companies and the AE community to build programs furthering the decarbonization and energy efficiency of the built environment. She has directly consulted on over 500 energy design assistant projects across the nation. Jeannie has spent the first half of her career designing affordable housing and care facilities. She brings her past experience in design and construction into her decarbonization consulting, helping participants find the highest level carbon reduction strategies that meet their project goals, design constraints, and budget. She is an active member of the AIA and a former co-chair of AIA Charlotte's Women in Architecture Committee. And during the presentation, please put your questions in the chat box and Jeannie will either answer them during the presentation or at the end. And so welcome, Jeannie.
Thank you, Dee. I appreciate the warm welcome and the great introduction. Again, I'm Jeannie Huntsman, and I'm here today representing the California Energy Design Assistance Program. For those of you who have participated in the old Savings by Design program, the new California Energy Design Assistance Program replaced that program. It's a free program that provides decarbonization consulting and incentives to help you maximize your new construction and major renovations projects' decarbonization potential. And you can enroll in CEDA by visiting our website at californiaeda.com. So the next slide here is our learning objectives and abstracts. I'm not going to go over that in detail other than to say that this course was approved for one HSW credit and decarbonization credit. So jumping into the presentation, why are we talking about carbon? On the left, you see that buildings account for about 40% of all the carbon emitted globally. And then on the right, we're really looking at how that breaks down between embodied carbon and building operations. So 28% of that carbon in buildings is used in the activities supporting the construction of buildings, and 72% is used in the operation of buildings. And so in this session, we're really going to focus on the operations of buildings and how we can reduce that 72%. So there's still a lot of work needed to be done on that piece. So I think a lot of us have heard those metrics before. And as a whole, as architects, we value sustainable design, but getting folks to execute sustainable design strategies is really hard. I know that in my design, I've heard a lot of thoughts about why something can't be implemented in a project, ranging from those that are listed on the list here. That clients aren't interested, the budgets are too tight, developers just don't care, paybacks are too long, the timeline is too short to consider options, we're moving too fast, the contractors aren't comfortable with it, so they're not going to install it, measures just get removed in value engineering, it's sometimes not really in our scope of work, or it's the engineer's problem to solve and it's just not required by code. But did we really solve our clients' design challenges if we turn over a building that could potentially depreciate at a faster rate than others in the market, has a lower net operating income or profitability, is more vulnerable to weather events, and at risk of becoming a stranded asset, or has occupant comfort issues? So we're going to really focus on how we can help solve some of those challenges. And also the incentive programs that are available out there can also help make the argument and build the space in the design process to have the conversation of what decarbonization strategies make the most fit for your particular project. And so during the call today, you're going to hear me talk about a few rules of thumb when considering energy and carbon use in buildings. And there are some good ones out there. But there's always a word of caution in that rules of thumb aren't static. every building is different, every owner, every user, and even the facility staff is different, which means the buildings operate and use energy differently. And with any of that, any of you that have been in this industry for more than a year or two knows that everything changes and the pace of change is kind of speeding up. So what we do today and how we design and the equipment we install might very well be different than was even a year or two ago. So if you'll indulge me a little bit to help me illustrate my point, I want to give you a brief history lesson about electricity. People have known about electricity since ancient times, but we've really only been harnessing its power for about 250 years or so. Things really took off when Edison brought electric lights to those who could afford it in the 1880s. My grandmother was born in the early 1900s, and she told me how magical it was when she got electric lights installed in her childhood home. And so if you start to think about one person's lifetime, you think about my grandmother, in her lifetime, lights were installed in her home. She got, as time went on, she got in her first house an electric washing machine and a refrigerator. The electric washing machine was a real time saver for her. And then towards retirement, cable TV came, and which was excellent because my grandfather was home a lot, and she thought that was a real lifesaver as well, since it entertained him and got him out of her hair. And then before she passed away, she was reading books on her iPad and keeping in touch with her great-grandchildren on FaceTime. And if you really put that one person's lifespan into perspective, how much electricity has changed one person's life in the span of a short 100 years. I think that's pretty amazing. So we've gone from electricity being a luxury for the privileged few to really being this fundamental human right and a necessity to our modern lifestyle. So how can we rely on rules of thumb when technology and the grid is changing so quickly? Another thing to think about with electricity is that electricity needs to be consumed at the moment it's produced because grid scale storage is still very costly and limited. We're making a lot of advancements there. But as consumers, we do not use or receive electricity in a constant stream. We demand it at different times by plugging something in or turning it on. And this constant fluctuation makes it very hard to predict how much energy to produce. To meet demand, utilities separate generation into two general segments, base load and peak load. The base load on the grid is the minimum level of demand on the electric grid over a span of time, for example, 1 week. The remainder demand is varying throughout the day and is met with systems that turn up and down quickly. System operators prefer a flat energy profile with a few small hills and valleys because it allows them to operate the system smoothly with the least cost. That's not the grid that we have in California. Widespread solar impacts the load shape California grid operators are seeing. It's got deep gorges and steep mountains. Shape is also often called the duck curve because it kind of looks like a duck. So between 4 p.m. and 7 p.m., there's an increasingly steep wrap up of demand, currently met mostly with natural gas power plants. That's what they call the neck of the duck. The solar output begins to drop right before the peak load of the day, around 6 p.m. So that variable solar needs to be balanced with either dispatchable power generation or flexible demand, since we don't have that grid scale battery power. So this scenario doesn't create a very profitable business model for electric companies, which impact rates. A few ways to solve this is to build load midday to raise the belly of the duck. Electric vehicles and electrification are some of those options, or to shift the load by incorporating grid scale battery storage, or reward customers who shed and shift off of peak demand. So today's energy mix in California is cleaner than the national average. It includes less coal, more renewables, and more natural gas. It will continue to decarbonize with non-dispatchable solar and wind. However, the duck curve is going to continue to grow as solar gets cheaper and is being mandated in certain building types by the Energy Code. So tomorrow's grid continues to evolve and it's getting a lot cleaner, sometimes at a faster rate than our buildings. And so use of coal and electric generation is being replaced with renewables and natural gas plants, and restrictions on new natural gas hookups are also popping up as well. And natural gas installation will no longer be subsidized in the state of California starting July of 2023. So the cost of gas infrastructure is about to become much more visible. And so we're starting to see new incentives to encourage electrification. Renewables are becoming more cost effective and technology is continuing to advance, making adoption easier and faster. We're getting closer to that utility grade battery storage and distributed battery storage. And all of this combined makes the grid of the future cleaner and more resilient than the grid of today. As the grid changes, so too will rate structures. Demand response programs provide financial incentives to reduce consumption during peak incidents. And time of use rate structures are starting to pop up where you pay per kilowatt hour charges throughout the day, with the highest charges happening during peak hours, encouraging customers to reduce the load when the grid really needs that relief. So jumping back to our rules of thumb for a moment, especially with that word of caution on making sure our rules of thumb are valid. When we're using rules of thumb, or when we rely on manufacturers' literature, or even comparing the energy profile of your design to another building, it's important that we're comparing apples to apples. So climate, building type, function, form and size, and even subtle differences like window to wall area ratio, hours of operation, and usage all have a profound effect on how individual energy or carbon reduction measures perform in a building. So on the right, we've listed some of the many building components that play into energy and carbon. Key point here is that they all interact with each other, and each component of the system can affect how we think about and design the other parts of the building. As I mentioned earlier, the pace of change in our industry, and a big part is really rapidly changing and moving faster. And a big part of that is the technology that we have available. On the slide are some newer technologies that are being focused on in the quest for decarbonization. And those include heat pumps, VRF systems, heat pump water heaters, and all electric kitchen equipment. So kind of a recap of rules of thumb alone won't solve this challenge, because electricity is relatively young. The grid is continuously evolving, and our current structure is not a sustainable business model, and the rates keep changing. And there are too many variables that impact energy use in a building for a one-size-fits-all solution. And building system technology keeps evolving and improving. So what worked today might not work tomorrow. So what's our pathway or blueprint you can use to work towards decarbonization on your projects? Good news is the tools we use to analyze how projects interact with the grid are advancing too. They've become faster and more accurate, more versatile, easier to use, and affordable than they have in the past, all of which allows us as design professionals to tailor energy and carbon measures to the building design and respond to the changing energy industry at a local level. I was just talking with someone earlier today that even 10 years ago, when I was practicing affordable housing, I would never even consider doing an energy model on that type of a project, because I couldn't find a tool that I, as an architect, could easily understand without digging in with some deep physics knowledge and maybe a degree in engineering to understand how to utilize it to get the answers we need. Computers have solved a lot of that, or software have solved a lot of that issue, and there's much better software available today. So I recommend doing a comparative analysis in early schematic design. What goes into a comparative analysis is just simple building geometry, high level, probably a massing analysis level of shapes is what could be utilized to get a good high fidelity energy model. The expected hours of operation, some assumptions on how the building will be operated and occupied, types of spaces, that sort of thing. An average weather file, and some minimum requirements that set the baseline, generally that align to the current applicable energy code. All of these factors combined together gives us a really solid energy model. And from there, we can start to test a variety of different measures to do a comparative analysis on which measures make the most sense, really to give a large order of magnitude idea of which measures will have the biggest impact to carbon and long-term energy costs to help us make an informed decision. So why use comparisons when models are perfect? Well, energy modelers our energy models are nearly 100% accurate, provided you can actually accurately predict three main variables: human behavior, climate and weather, and energy prices. They also become more accurate the later in design and into occupancy. Early design models aren't intended to predict energy use so much as they're intended to help us make informed decisions. So where do we begin? We've kind of got a four-step process that we laid out here. First, starting in schematic design to really minimize the load as our first priority, thinking about the massing, the glazing, insulation, and the general HVAC concept. These types of strategies have a 20 to 70 year lifespan and are going to be in the building for a long period of time. So if we can minimize that load at the very beginning, we're off to a great start. Then implement simple and cost-effective systems for your HVAC design, lighting, daylighting controls, those sorts of things. Those items have 5 to 15 year lifespan, but could still reduce the energy costs of a building. And then only when you reduce your building's footprint as much as possible, should you consider alternative sources of energy such as solar, wind, and cogeneration that have a 20-30 lifespan, since you've now reduced the base load low enough to make those items more cost effective and less impactful to the grid, helping you avoid some of those higher peak load charges. And then at the end of the day, we need to remember that people run these buildings, and they're going to run these buildings in ways we've never imagined. So thinking about it, there could be additional energy savings through shifting some of the operations of the building once it's been constructed. And we're not going to focus so much on this fourth bucket, but know that can shift and change what the assumptions were in the early energy model. We're going to instead focus on those first three buckets. All right, so from here, I'm going to jump into some decarbonization strategies or case studies. And these are some of the projects that we've looked in the California market. We've got a sample apartment building, a school building, K through 12 sort of building, office building, and a clinic. And they all have sort of typical office spaces, typical spaces that you generally see in those types of buildings. 100,000 square foot program with standard hours of operation. We've modeled both of these projects, or each of these case studies, in both San Jose and Los Angeles to see if there's some differences there. Just noticing we had a question pop up. What is VRF? It's variable refrigerant flow. It's a type of HVAC system that has refrigerant lines running around your building, connecting these small cassettes that provide heating and cooling. And why that could be a valuable system is, one, it's an all-electric system, and two, it provides individual controls. And those individual controls let you manage occupant comfort a little bit differently. It's also a very slim system, so it can work really well in existing buildings or retrofits. So back to the case studies. jump in here to, we've modeled them in San Jose and Los Angeles. And for each of these buildings, we've looked at it with 3 different HVAC systems. We've got an all natural gas, primary natural gas system with the heating and the water heating being served by natural gas, and the other piece is electric. So for all the buildings, it's a VAV system with an air-cooled chiller and a gas boiler. Pretty typical what you'd find, except for the apartment building where we use some Magic Pack systems, self-contained systems in apartments with the packaged rooftop unit in the apartment common spaces. And again, those gas-fired water heaters. For the electric system, we switched out that system with air source heat pumps with electric backup and electric resistance water heaters. And then for the more renewable option, we threw everything at it and we looked at ground coupled water loop heat pumps and heat pump water heaters. I'm going to throw a caveat: soil conditions in California in all areas don't always make ground coupled water loop heat pumps the best fit, but we still looked at it from the model to see what the impact would be. Following is some mechanical system assumptions. I'm not going to read all of those, other than to say that demand control ventilation was included where applicable, and then that really we set all of these up with the same efficiency levels. And then architectural assumptions were that the envelope was slightly above code minimums, including aluminum windows in all of the buildings except for the apartments where we had vinyl windows. And then lighting assumptions were we were assuming utilizing LED lights throughout, since that's pretty common these days, and lighting controls were as required by code. So what's the carbon impact by system if we're looking at each of these prototypes? So I've broken down this information into a chart format for each different case study. And so this particular case study is the multifamily building located in Northern California, so in that San Jose area. And for the first sort of set of 4 bar charts, we looked at what is the annual emissions, carbon emissions from this building if it was on today's grid. And we looked at what is the worst, in the gray bars were the worst performing building we could possibly have done, natural gas sort of system to meet the bare minimum of the code. The orange and yellowish bars are what that building would be if they were the natural gas or conventional gas system that I described earlier. And then the blue bar is that air source heat pump system I described, and the green is that ground coupled heat pump. And so you can see that if you just looked at today's emissions, the all electric system is going to have less emissions overall than the natural gas systems. You could still get some good savings from a natural gas system compared to the code level. But what you're going to see is if we look at this, how the grid is going to change over time, that really you're stuck with the carbon emissions of the gas heating and water heating. You really can't make any real reductions in that without changing out the system. And the all electric systems are going to have less emissions because the grid is getting cleaner over time. So that next set of bars is what would be the average emissions over 30 years based off of already in progress grid updates. So how is that grid changing, and how is that change going to happen over 30 years? And then the estimated annual emissions for 2050 takes a look at the Cambria studies that are being done by the national labs to determine what are the different scenarios that could happen in each of the states for what that electric grid should look like in 2050. And we sort of took a middle of the road option, not the most efficient, to kind of show middle of the road, where would this building be at? So where would this building land if it was looking at 2050 emissions, where we think the grid is going to be at that time period. And then a question on what is a ground couple heat pump system? That's a geothermal type system. So it's a standard heat pump that's connected to a geothermal loop outside the building. So if we look at the scenario for multifamily in Southern Cal, the charts are all the same. You see the emissions get a little bit less overall, but the scenario is still the same, where the natural gas systems are going to be kind of stuck by the time we get to 2050, and you're really only getting to those low emissions with the all electric system. And that's going to be a trend we're going to see throughout. Now, if we look at the K through 12 school, we see that similar trends, similar setup here. A larger efficiencies can be had from the baseline worst performing code building to a natural gas system, but then further reductions in emissions can be had if we consider an all electric system. And we're going to dig into each of these a little bit deeper, but I'm just trying to set a framework. Again, SoCal, slightly less emissions for a K through 12 school than what we saw on the Northern Cal, but still a similar trend. And then if we switch to an office building, office buildings have a little bit less of a total carbon emissions than the K through 12 or multifamily buildings. However, still the all electric system does play out better in the 2050, but things are a little bit closer and a little bit more in the noise for the office buildings. So maybe some focus on some plug loads to really help decarbonize would be important in those types of buildings. And then the office in Southern Cal, very similar response here. What's interesting is with cooling loads, the air source heat pump system sort of peaks out with a little bit less carbon emissions today, but really kind of within the noise, the models all pretty similar. So there might be other areas of focus, and we're gonna dive into what those other areas might be in a bit. And then if we look at the healthcare type of building, we see that there's not a whole ton of natural gas usage in a healthcare facility. And that's because there's a lot of heat output from the equipment that's in the building. So there's maybe less heating use in that type of a building. And really it's the drive of the energy use and the carbon emissions is from the electrical life-saving equipment. So you're going to see very similar impacts across the board for the healthcare, but by 2050, the all electric systems are still performing better. However, they're not as don't have as big. If we were going to focus on one building type today, I might, to really drive lower carbon emissions, I might choose a multifamily over healthcare. And then similar scenario again for that healthcare system in Southern Cal. All right, so some key takeaways. Installing natural gas equipment in new buildings locks in the carbon emissions for the lifetime of that equipment. And the electric grid is getting cleaner each year, which has a profound impact on the carbon emissions of the built environment. So installing efficient electric equipment will allow the building to decarbonize along with the electric grid. And electrifying buildings is key to decarbonizing the built environment. So you may be asking, so what is the impact of solar? So with solar, there's kind of a diminishing return on carbon savings over time for PV, but it's still really important strategy for reducing energy costs. If you look at this chart, this is the going back to that multifamily building in Northern Cal. What we did here is we took the baseline and indicated which areas were natural gas and then what was electric. And then from those electric emissions, we put a standard solar array, kind of maxed out the rooftop of this particular building for the multifamily, and put in as much solar as we thought we could fit on the project, and to see, what was that renewable generation offset to the electric load. So from there, we've identified that the all electric options, have a similar reduction in the solar as the gas, because we're focusing on what the electricity, the PV only impacts the electricity. So as you can see, as the grid gets cleaner, the emissions that are avoided from the solar get smaller, and so the impact of solar from a carbon emission standpoint reduces. Again, really the energy cost savings of solar is really important for balancing customer long-term energy costs, but it might have a lower reduction on emissions. So solar is really not our easy button to getting to carbon emissions. I do see, I'll take a quick break here and say that there's a question in the chat on natural gas bans in California cities stood up to legal challenges. I'm leaving that one to the courts. There's a lot of hype about that in the news. I do know that the California Public Utility Commission is no longer subsidizing natural gas costs, and that's within their right to change. And so that would be the key consideration that I would leave you guys to focus on. I encourage all electrification where it makes sense for a building project. And certainly it's something that we can look at if you enroll in one of our free programs that's available to look at decarbonization of your particular design project. The gas bans are very interesting. They've been done very differently across different cities and everything. So I won't dive into the legality of it because I'm not a lawyer, but it is an interesting question. But the point I do want to make sure everyone's aware of is that the cost of natural gas hookups is going to become greater because they're no longer being subsidized. And that's not part of the challenge. That's a decision by the California Public Utility Commission. So again, going back to solar, solar has a diminishing return on solar from a carbon standpoint as the grid gets cleaner, but it's still a key strategy for reducing annual energy costs and is required by code by certain building types. And electrifying as many end uses as possible first helps you receive the maximum benefit of solar, and battery storage paired with solar will be an important strategy for operating cost reduction in the future. So let's take a quick look at how each of these building systems impact carbon from a system standpoint. So what we've done here is we've taken the multifamily building in Northern California and we've broken it down by the carbon emissions by end use. So what I mean by that is the different systems in a building, how do they impact the overall carbon emissions? And so that red line down at the bottom of the chart is the heating usage and the carbon emissions from heating from a multifamily building. That blue line is going to be the emissions from cooling. And then fan energy and ventilation is the gray line. And that big green chunk is the service water heating. And so really, if you think about what is the biggest carbon emission in a natural gas multifamily building, it's going to be that hot water heating. So if you have a choice between which end use you should electrify, focusing first on the hot water heating will have the biggest impact to overall carbon emissions. The next little dark yellow line is going to be lighting, and that top sort of lighter yellow, brighter yellow line is going to be the plug loads, the computers, laptops, TVs, whatever you plug into building, refrigerators, that sort of thing. And that's going to be that usage. So you can see with the natural gas system, you have a really high impact for water heating. If you switch to an electric resistance system, the carbon emissions is going to be a lot less, but there's still a pretty decent amount of emissions there. What's interesting to me is if you switch over to that more renewable system, you can see that the green bar has shrunk quite a bit from the previous bars. And that's because in that particular building type, we've installed a central heat pump hot water heater. And that central heat pump hot water heater has some really good emission savings. So if we pulled that central heat pump hot water heater and stuck it into the middle scenario with the air source heat pump, changing that out from the electric resistance, we'd really see a huge reduction in carbon emissions. What's also interesting here is this ground source heat pump system has a lot of fan and pumping energy that the other systems didn't have. So it's really providing more carbon emissions impact from the HVAC side than the air source heat pump. So I'd say if we're really going to maximize the carbon reduction of a multifamily building, you put in those air source heat pumps in the individual units, and you do a central heat pump water heater and forgo that geothermal system. Again, similar thing in the Southern California area, except the heating load is pretty minuscule and the cooling load has gotten a little bit higher. But really that key focus is reducing the carbon emissions on the water heating. Different scenario in the offices, and I think in this one we'll get to the schools a little bit later. Must be slightly out of order, but in the office buildings, you can see there's a little bit more of a heating load, but a large driver is going to be those really plug loads, the computers, data centers, and things that are in an office building. If we look at the air source heat pump scenario, we see there's a large amount of fan energy. I think there the distributed air source heat pump system is really not the best system for an office, and consideration of something like a VRF system or a standard VAV system paired with a heat recovery chiller might give you more carbon reduction than this distributed air source heat pump system. So that might be another HVAC option that could really get you to the maximum benefit. And so what I'm trying to illustrate is through analysis that even the systems you might think would be the best fit, like a geothermal system, might not be the best fit for that particular project. And so an analysis can help you kind of figure out what's your best fit for that particular building. Again, looking at this office in Southern Cal, an increase in cooling usage and a reduction in heating, which drives those that fan energy up for the air source heat pump a little bit further. K through 12, in this type of a project, really there's some even load distribution for carbon emissions between all the different end uses. So there you may want to sort of tackle it all, but there's some good savings to be had switching from a conventional gas boiler VAV system to this air source heat pump or geothermal. And then looking at the water heating usage of this building, this particular project had a significant number of showers. And so, you know, it made sense to think about carbon reduction of the water heating as well. That may not be the case in every school project. And there's still quite a bit of load here on the plug loads, and then lighting is still an opportunity, which you're not really seeing as a big opportunity in some of the other building types. So it's an area to focus on, and some improvement could be had there. Similar scenario in K through 12s in Southern California, but heating becomes less of an issue to consider. And here, really thinking more about that. How do we reduce that fan energy? Because that's becoming more of a critical factor. And then in the healthcare I think this illustrates for you that really those plug loads, the life-saving equipment, is really the driver of the energy use in a healthcare facility. It's not necessarily the heating and cooling. However, there is a lot of fan energy, ventilation loads that are in air changes that occur in a healthcare facility. And so that's an area where some additional review could be had of how to reduce the carbon emissions within the confines of ensuring that building stays operational for its needs and meets the applicable codes. And the same similar scenario in the Southern Cal. So key takeaways here are that water heating is the biggest carbon usage in apartments and school facilities. Plug loads and fan energy in offices and healthcare are opportunities for carbon reduction, and there's minimal savings impact left from lighting, as LEDs have made electric lights very efficient. And then the next 5 years, just as a fun fact, there's going to be 460 million square feet of new construction apartments expected to be built in the state of California. So that's why I kind of focus on that particular building type as a key opportunity. I'm going to fly through some of these other considerations real quick, just kind of noting that reminder that the commercial building that you build is going to be around in 2050. And so what you put in today is going to impact the grid of tomorrow. And likely your HVAC systems might only get a change out once or twice during that time period. Water heating might have a couple of more replacements, and electric lighting will have a few more, but those envelope systems are going to stay with the building for that lifespan. I'll skip over those pieces. So building envelope and impacts heating and cooling loads and has a long lifespan. And additional carbon savings can be found by striking a balance between envelope strategies and project budget and goals. And additional carbon can be found when we analyze the impacts of some of those internal loads that are in a building. And decarbonization analysis can help us identify areas where additional savings can be found. So overall conclusions, start early, minimize the load as the first priority, install simple, cost-effective systems, use appropriate energy sources, and then at the end of the day, hopefully folks will operate the building well, but it might be an opportunity for us as architects to get more involved in what's happening on that stage. So the landscape of power generation is changing and contributes significantly to carbon reduction. It's important to utilize energy modeling to explore load balancing and carbon emissions, and also to assess carbon reductions with today's emissions as well as future emission rates to design buildings that are built for the future, and really make that commitment to low carbon design strategies in the development of every project. And that was what I had for you guys today, so I'll open it up for questions.
Thank you so much, Jeannie. I think if people want to unmute themselves, they can just chime in with some questions. We have almost 15 minutes left.
Jeannie, could you talk more about ground source heat pumps and where they might make the most sense? I've done a couple systems like that in the most severe climate zones.
Yeah, so ground source, I see a lot of them in Iowa. So what's nice about that is there's severe sort of heat and then severe cold. So that sort of change in temperature helps. It really depends on soil conditions. So you really need to get some borings done on the site if that might be a good fit. But before you go through that trouble, I recommend doing this sort of carbon analysis to really think about because it's a lot cheaper to do the carbon analysis. It's free from the utility if you're in one of the participating service territories, than it is to go out and have borings done and get that far down the road. So it can be a really great system where it makes sense, but you really need to think about how you're using the building, hours of operation, the loads of the building, and then doing that early energy analysis to test different systems to see if it's going to get you the carbon emissions that you want before you go down the road of really thinking about installing it. But it can be a great system. I've seen a lot of them in the Midwest. A few of them scattered across California. Our work in California is a little bit newer, so you might actually have more experience than I have in where they make sense in California, and a little bit in the Carolinas. I've seen some of the ground source heat pump, but not in every area.
I'll just mention that I did one into a body of water, so there was no boring. Yeah.
That makes a big difference. So if you've got the water, it does help, particularly with costs.
Hey, Dennis, how did that work? Did you run the loop out into a water system or a lake or something?
It wasn't a lake, Michael. It was the Sedgwick Reserve, and there were these old brick-lined water tanks underground. So they were in the ground, non-potable water. So we ran loops and coils of pipe into those, and the temperature stays pretty constant all year long.
Yeah, cool. We just did one of these geothermal ground coupled heat pumps on top of Tunnel Road in this all electric house. Those things are pretty amazing how they it's about 62 degrees when they get down there. So it's even functions up in the foothills of Santa Barbara here. Pretty cool.
Yeah, they can be a really awesome system. When I was living in Iowa, I was considering them for my own house. Then we moved to North Carolina, and now I've just got a standard heat pump system, and I am saving so much energy with a heat pump water heater and a just a general air source heat pump on that building compared to the rental house we had, which was similar size, newer construction and better envelope, but with a gas furnace and a gas water heater. And I just couldn't believe how much energy savings I'm getting from the heat pump water heater. It's probably the best purchase I've ever gotten. Plus it connects to my phone, and so I can monitor the temperatures and those sorts of things. I just love it.
So in a single family house, would you go there before space heating?
I would. Personally, and I will admit, my old all electric water heater that was in this house was from the 90s, so it was not performing at peak function. I think the previous owners let it go too long, but I'm saving $40 a month, and that's with lower energy costs in the Carolinas than you guys have in California. So, I can imagine that you would see greater impacts to that. I just really love, I can't say enough good things about my heat pump water heater. Plus I get some free cooling out of it too, which is really awesome since it's so hot, particularly right now.
Where is that located in your house, the water heater?
It is in the crawl space, but right next to the air source heat pump sort of intake. So the air coming into the air source heat pump for the HVAC is cooler in sort of in the middle of the house, in that crawl space, so that it's not as hot as the surrounding areas. But that I have seen a noticeable difference in how hard the HVAC system has to work now that we installed that. And when you go underneath the crawl space, it feels more like a basement in comfort level than the hot messiness that it was before. And it had some great benefits for dehumidification as well. So we have less weird smells in the crawl space as well.
So it's outside of your envelope then in the crawl space.
Yep. And I'm in Charlotte, North Carolina, so that's pretty temperate, but very humid.
Mm-hmm.
So.
And is solar on your radar for your house?
It is. We've got to replace the other aging HVAC and infrastructure systems first before we get to solar, but also battery backup, so that we have power in the event of power issues, because we have a lot of downed trees because we're very wooded here.
Something that was recently discussed is, and this is for single family residential, is pairing solar with a electric vehicle that has a bidirectional battery.
Yeah, I think that's really interesting work. A cool project that I'm seeing on the commercial scale that they were testing out here with Duke Energy was they were taking school buses and giving them to the community as a test with this sort of large electric battery storage, and then pairing that with a solar canopy for where the school buses sit. So then they could be deployed as emergency power generators in the event of a power failure. And I thought that was cool because the community gets this school bus that's not used very often. So it's usually very well charged and just sitting ready and waiting to be deployed as emergency vehicle. So I thought that was a cool study, and I'm hoping more utilities do that pilot.
Mm-hmm.
Hey, Dee, what was that battery that you just mentioned?
Electric vehicles, some of them come with bidirectional batteries. So you can, if it's the end of the day, and the duck curve is, there's your costs are going up and there's a bigger demand on the system, you can pull power from your car.
Oh, I see. Okay, so yeah, you can charge your car by plugging it in from your house, or you could charge your house by plugging it into your car.
Right.
Yep.
And
That's pretty cool.
And from what I was told, and this was when we had that talk by Dave Intner, was that if you hook your house up to your car battery, it's really not going to it's not going to like drain your battery. It's going to pull it down like very little. Is that what you recall, Dennis? I think you were there.
No, I missed that one.
Oh, okay. Yeah, I was surprised. I thought it would kind of drain the car battery pretty quickly, but it really doesn't.
Dee, this is Suzanne Tejada. I was there, and that I'm confirming what David Ittner said. Yeah, it's really minimal.
Yeah.
Yeah, I think you can see the larger costs with these time of use rates during those periods. So if you're trying to reduce your energy costs and make things a little bit more affordable, if you can do that during those times of the day where they're going to be charging you more because of those peak loads, you can really have some great cost savings. So I think batteries are going to be a big component of energy cost savings in the future.
Mm-hmm. There are several cars that have those right now, like the Ford Truck Lightning and the I forget the other one that does, but I was told in a couple of years there's going to be a huge variety of cars that are going to have that available.
I wasn't sure I wanted to wait, so I signed up for the Tesla Powerwall from Swell. It's costing me about 9,000, I think, which it hurts. It's a lot, but I like the idea of having the backup power too.
Mm-hmm. Wonderful. Great. You can let us know how that works out.
Yeah.
Do you have solar, Dennis?
I do. Not a lot. I've got 2.5 kilowatts.
Mm-hmm.
But my understanding is I'll be able to manage, feed the battery during the day and then work off the battery at night and maybe keep Edison out of my house altogether. I don't know.
That's a good goal.
Yes.
Yeah.
There's a lot of change going on in the energy industry, and those sorts of strategies are really popping up more frequently. And I think we're going to start to see some good case studies come out of that.
Hey, Dennis, did you hear about the grants for the Tesla Powerwalls?
Yeah, I think I'm taking advantage of all of them. I hope. This was the city-sponsored Swell Energy offer.
Okay. Yeah, I was right to the end with one of the state ones, and we got approved and it was all ready to go. And then they said, oops, we just reclassified it. Only low-income people can receive the grant. So it was like after we were approved and ready to get, I think 2 of those Tesla Powerwalls in, they said, no, we're only going to give them to the low-income people around the state. So I didn't know if that, and then it went away. The guy said, "Hey, sorry, the government, Newsom just changed his mind." Because I thought it was a good idea just to get it out to as many people as you could, but they reclassified that last year. This was last year. I was almost there, but good. Yeah, let us know how it works. It's a cool
Yeah, I
concept.
will. Yeah.
Wonderful. Well, thank you everybody for attending, and thank you, Jeannie. This was wonderful. It
Yeah,
was
very helpful.
really great. And I just have a quick announcement. Early bird tickets are going on sale today for the architectural tour in October, and it's going to be announced in today's AIA newsletter that's going out.
Good. Good.
Great.
Awesome.
Bye.
Thanks,
you.
everybody.
Thank you.
Bye-bye.